So in the first part of these lecture notes, we have seen the definition of extended Borel functions, which will be the central object of study from now on in the rest of this module. Then we saw a criterion for when a function taking values on the extended real line is measurable, which means it is an extended Borel function. And now we move to the last part of this video lecture, which is the pullback of Borel sets and how can we characterize now measurability in terms of this pullback. So again, an extended Borel function is nothing but a measurable function from a certain source space, omega 1 f1, to the target space extended real line with Borel sets. What is usually called Borel function in some textbooks is simply an extended Borel function that never takes infinite values. So we focus on extended Borel functions because this makes the theory a little more general. And we have seen these equivalent conditions that we can check of a certain function to conclude that the function is an extended Borel function. So what is the pullback of the sigma algebra given by the collection of Borel sets of the extended real line? So here's a lemma that tells us exactly what it is. So the sigma algebra generated by a function f, which is the pullback. Remember, when we have two spaces omega and the other space, it is now the extended real line. If we have a function f and we have a sigma algebra here, which is the Borel sets of the extended real line, then we can define the pullback of the sigma algebra. This would be sigma of f, which is given by the pre-image of all sets in this sigma algebra of the target space. Now, how can we prove this lemma? So let us recall a remark from the previous lecture, which it said a sigma algebra G, for a given sigma algebra G on omega 1, the function f will be G f2 measurable, where f2 is the sigma algebra of the target space omega 2, if and only if the sigma algebra G contains the pullback of f. So again, let's do the diagram again. If we have omega 1 and then it has a map to omega 2 by a function f, if omega 2 has a certain sigma algebra f2, so then we can do the pullback of the sigma algebra f2 and we can get the sigma algebra generated by this function f. We have seen already in the previous lecture that a class of a family of sets G, if and only if it contains the sigma algebra generated by f, that's the condition equivalent to f being measurable. So f will be G f2 measurable if and only if G is finer than the sigma algebra generated by f. Now we use this remark imported from the previous video lecture to prove this lemma here, and this will be done if we combine it. Let's go back a few more slides. If we combine it with this key lemma from the first part of this video lecture. So what are we trying to prove? That the sigma algebra generated by f is the same. So this is a completely different object. This is the pullback of a certain given sigma algebra on a target space, which we want to be the Borel sigma algebra of the extended real line. It will be the pullback by the function f of the Borel sets of the extended real line. So the sigma here means this, and this sigma here is just the family of sets, the sigma algebra generated by a given family of sets, and here's the family of sets. It's the family of the pre-image. So this is just a notation for f minus 1 of minus infinity a, which is the same as omega such that f of omega is at most A. So this is just a notation. And we want to prove that these two sets are equal, and we're going to prove this using a typical way of proving two sets are equal. We prove first that sigma of f is a subset of the sigma algebra generated by this family, and then we prove the opposite inclusion. In fact, let us prove the reverse inclusion first. So we let A be any real number, because we are making a claim about sets of a family that is indexed by real numbers. Let A be any real number, and just we note that since this closed interval here, minus infinity A, is an element of the Borel set of the extended real line, then by definition of the pullback of a sigma algebra by the function f, we have that the pre-image f minus 1 of this interval closed at infinity, this is a member of this sigma algebra sigma of f. So we can conclude from this that this family, the family pre-image f less than or equal to A, this family that is indexed by finite A, is contained in the family sigma of f. So this notation again is for a family of sets in the source space. And so if we define G to be the sigma algebra generated by all this class of sets, well, this is still contained in the sigma algebra generated by F, because we know if a family, this was an exercise from chapter 2, if a family is contained in a certain sigma algebra, then the sigma algebra generated by that family is also contained in it. And this gives us what we were trying to prove, which is the inclusion in this direction. Now for the inclusion in the other direction, we use again the same definition that we made for this family G, and we note that, let's go back here, since the pre-image of these intervals from minus infinity to A is a member of G for every A real, this follows from the previous lemma, this lemma here, from a previous part of this video lecture. It follows that the function f is G/B of R extended measurable. And now the final piece to conclude the proof of the lemma. Let us go back here one slide. It will be this remark here, which says a function is measurable if and only if the sigma algebra of the source space G, it contains the sigma algebra generated by F. So we conclude here, since we know already it is measurable, so we can conclude that this family G contains the sigma algebra given by the pullback by the function f, which is exactly the odd inclusion we were trying to prove. This concludes the proof of the lemma.